Ladies and gentlemen, class recording has started. So, yesterday, starting on Monday, and then continuing on yesterday, we started in on the kinetic theory of matter. And we said the kinetic theory was used to explain why matter exists in a certain state of matter. And we said that when it's all said and done, there are two factors that go into determining what state of matter something exists in. What are the two factors that determine the state of matter that something exists in? Katie, what's one?
Motion.
Motion of the particles. And then, Maddie, what's the other one?
The forces of attraction.
The forces of attraction. So, if we're going to account for the state of matter that something exists in, we have to look at the motion of the particles and also the forces of attraction between them. That being said, if we're going to look at changes of state, that also means we're going to have to look at those two factors. So, starting off, first, just quick definition. Here's a little triangle. It shows you three states of matter. We got some words there. We're going to come to those words again. But changes of state are when, or phase changes are when substance changes states of matter. Duh. I hope that wasn't too earth-shattering for you. Okay? But more importantly, changes of state are reversible physical changes. Earlier this unit, we talked about chemical versus physical change. If something is a physical change, what does that mean? Physical change. If something is a physical change, what does that tell us? Far good. The substance doesn't retain its properties. The properties will change. Like when water melts or when ice melts, right? Sir?
The properties change, but the components stay the same.
Good. Instead of components, how about composition? Okay? So the properties are going to change, but what it actually is, the composition, does not change. When water goes from being an ice cube to being a glass of water, it's still two hydrogens chemically bonded with one oxygen. Does it have the same properties? No, but it's still the same stuff. So that's a phase change is a physical change. Okay? Now, if we're going to talk about that, here's the big key for today, right? Significant energy changes. During a phase change, energy is going to be transferred between the substance and the surroundings. Okay? There has to be some kind of energy change between substances and surroundings. If we relate some topics back to a really old concept, one we talked like back in September maybe, right? That could be the definition of what? A really old word that we came across a long time ago. I heard it somewhere.
Work.
Work, right? Because work is a transfer of energy. Is it work like we talked about it? Not exactly, but the energy is still changing, and that's kind of the key with work. Okay? So, for the next 5 minutes, you don't have to write anything down. I want to talk about some things up here, and then we'll fill in the outline as we go along. Okay? So, that being said, let me go here, and let's go here and here. Okay, let's talk about one specific phase change, that being melting. When something melts, what happens? Ready?
It goes from a solid to a liquid.
Goes from a solid to a liquid. Based on our ideas of kinetic theory. That means a couple of things have to happen when something goes from a solid to a liquid. What's got to happen if something's going to go from a solid phase to a liquid phase? Betty, what's one thing?
The particles gain more energy.
Particles gain more energy. Sveta.
It has to do with heat.
It has to, well, that's the particle gaining more energy, right? Heat is a form of energy, okay? What else? A couple other things. Talk about those particles. Betty, what else?
They change in size.
Change in size is not exactly the right description. Somebody else want to take it? All right, sir?
Their speeds change.
Their speed change, so that they speed up, right?
The way
Becca?
they move, like how the liquid takes the shape of what container it's in, and how the solids takes its like definite shape.
That's more a property of things in a liquid phase. But what has to happen to the particles to make something go from a solid to a liquid phase? They have to speed up.
They have less attraction.
Less attraction for one another, right? Those are the two big things, and there might be one other thing. What do you know about how close particles in a liquid phase are? less close or less ordered, right? So when something goes from a solid to a liquid, particles become less ordered. Once again, we'll go through this again in a second, right? Molecules are going to vibrate more quickly and gain enough energy to break free of those fixed positions that they're in a solid. What has to happen? How is this going to happen, though? So, Savannah, you said what has to happen? It has to heat up. Heat is a form of what? We have to do what with energy to make this happen? Does it have to go into the substance or come out of the substance? What do we call it when heat goes into things? That is an endothermic process. Okay? Now, on the other hand, okay, don't worry, we'll fill it all in, promise. Okay? On the other hand, let's talk about freezing. What happens when something freezes? Okay? Liquid to solid. Based on kinetic theory things, when something goes from a liquid to a solid, what has to happen? Based on particles slow down. Emily, is that what you were going to say?
Well, I would say energy is
Okay, I would like to save that for the end. Particles slow down. What else has to happen?
It has a definite shape.
That's because what did the particles start doing more often to each other?
Attraction.
They attract each other, so forces of attraction increase. What about the space in between those particles?
They get closer.
Get closer together, right? So, particles more ordered, particles move more slowly, hold on to each other more forces of attraction, okay? Did you say? Did I tell you to hold on? Oh, Beck said, okay. Oh, Emily said. So, Emily, what has to happen in order to make all of these things happen?
It loses energy.
And what do we call that when a substance loses energy? That is an exothermic process, all right? So, going back to your outline, okay? Going back to your outline. Hold on a second, seeing how I'm recording this, let me actually pull the outline up so that people watching don't get confused.
How many people do you think actually watch this video?
Somebody, I just got a comment yesterday on one of my videos. It was the single replacement reaction when we had the zinc in the test tube and added the hydrochloric acid and it like bubbles and then we do the pop. Some random person just commented on it yesterday and said, "Hey, I did this in class today. It was cool." Swear. Because my YouTube account, the one that I put up all the class recordings on, is linked to my school email address. So whenever somebody comments on something, I have like 16 or 17 people subscribed to my channel.
Nice.
Just saying.
Just saying.
If you aren't one of them, maybe you should get on board. Get on board, all right? So let's take a look at this. All right. And so on the front side, hold on. All the people that subscribe to me are going to unsubscribe now because this video is not so hot, but whatever. All right. Let's go here. Okay. So on your outline. So letter B, underneath Roman numeral number 2. Endothermic means energy goes blank, the substance from the surroundings. Energy goes into, right? When something is endothermic, that means we're putting energy into it. What do we call that endothermic process when something turns from a solid to a liquid? That's melting. Right? What did we say happened to the particles? They do what?
So less ordered.
Less ordered. Okay. What else do those particles do?
Vibrate more quickly.
Migrate more quickly, or we can just kind of say move faster. Right? Vibrate more quickly, move faster, same thing, right? And then now, because of that, because they break free from those attractions of the other particles, what are they no longer in? Fixed positions.
With definite shape.
Or we could say definite shape, that would be fine. Or I would say orderly arrangement. Any of those things would work. Skipping down a couple. When something is exothermic, energy is blank to the surroundings from the substance. Energy is released.
Just kidding.
Okay? Exited, released, whatever. Okay? What's the exothermic process we discussed when something turns from a liquid to a solid?
Freezing.
Freezing. What happens to those particles? They become more ordered, or more orderly, or more orderly. Okay? The average energy does what? Decreases. And that causes the particles to move slower. Right? Then on the back, right? What do they start to do more?
Yeah.
Not react. They start to attract, right? They start to attract each other more, move less freely. Yeah? Good there? Yeah, I do. I'm sorry. All right, it's good with those?
Yes.
Now, if we go back to the very first slide that we did today, that triangle up in the top left-hand corner of the front side of your page, what do you know about the energy of a solid versus a liquid versus a gas? Which particles have the most energy? Gases. Which ones have the least energy?
Solids.
So any time that the energy has to increase, we already talked about when something moves from a solid to a liquid, particles' energy has to increase, and we called that what kind of a process? That's not exothermic, endothermic. There's two other endothermic processes here. What are the other two endothermic processes? Vaporization, when something turns from a liquid to a gas, and sublimation, when something turns directly from a gas or solid into a gas. Because in both of those cases, you have to increase the energy of the particles. Okay? Can something turn straight from a solid into a gas? Sure. You ever see dry ice before? That's what happens. Okay? But then on the other hand, what? Sorry. You ever seen dry ice before? It's a big chunk. It's a big chunk. It looks like ice, but it's actually carbon dioxide, and it's solid. It's really cold, but it doesn't melt. It just like bubbles away. Kind of like looks like. You ever like at Halloween time have? Yeah, you can. They sell it at Mitchell's. But you ever have like punch that like kind of bubbles and gurgles and there's like. Get on board, man. Go to a Halloween party next year, right? Sorry.
I'm good.
Wait a minute. Maddie, it goes straight from a solid phase to a gas phase without actually melting. So it's kind of good at. It's good for.
Examples.
It's,
Is
for
that what you melt snow in? That's salt, right? That's rock salt?
yeah, not dry ice though. It's actually good. It's actually good for dry ice. Is actually really good for shipping things that are frozen. For example, I just refinanced my house and got a new mortgage, but the mortgage company took a long time to like do our stuff, so they offered us like a free shipment from Omaha Steaks. Anybody know Omaha Steaks?
Awesome.
Yeah.
I'm jealous.
So they sent it to us, but when it gets to our house, it's frozen, but there's nothing inside of it because they pack it in dry ice, so it stays cold for really long. But when the dry ice gets warm, as it gets shipped, it doesn't melt, so you don't end up with a bunch of water. It just goes away. So it's actually really good for shipping. So, you know.
Fun fact.
And we got free Omaha Steaks. So. All right. So, but on the other hand, right, when something goes from being high energy to lower energy, we said what has to happen there? Energy has to be what? Released, or we call that exothermic, right? So what kind of exothermic changes are up here? We already talked about one. What else, Betty? Condensation, when something turns from a gas to a liquid, or deposition, when something goes straight from a gas phase to a solid phase. Doesn't happen real often, but especially like on a really cold night, when you get like frost, okay? Not like on the grass, but like when there's frost on the window, okay? That water vapor in the air, it doesn't form a drop of water on the window and then turn into ice. It just goes straight to the ice phase. So if it's already a cold night, what do you know about that water vapor in the air anyway? Does it have a whole lot of energy? Less than like when it's 100 degrees outside, right? So it's easier for it to lose that energy and go straight to the solid phase. But it doesn't form like a drop of water on the window first and then freeze. It just goes straight to the solid phase. All right, good there? Okay. In case you haven't done this already, right, there's a couple spaces on here that we didn't fill in together, right? And so when something, other endothermic changes, vaporization, when something turns from a liquid to a gas, that could be boiling when it happens at the boiling point, or it could be evaporation if it happens a little more slowly. Sublimation is when something goes straight from a solid to a gas. Those are both endothermic changes because it involves putting energy into something. But on the other hand, right, the exothermic changes, condensation when something turns from a gas to a liquid, or deposition when something goes straight from a gas to a solid. Good there? Okay. Next, let's talk about the next picture that shows up on your outline, which is the heating curve for water. You guys did something similar to this yesterday, but yours wasn't a heating curve. What was it? A cooling curve. So what does it look like? It's like flipped over, right? It starts high and goes low as opposed to starting low and going high. But if we take a look at this graph, right? X-axis, what are we looking at? Heat added, which is a fancy way of saying what? Energy. And then on the y-axis, we have temperature. Does anybody know what temperature is really a measure of? We haven't talked about this formally in class. We're going to do it next week. But what does temperature tell you about?
How fast the particles are moving.
Temperature tells you about motion, how fast the particles are moving. We'll talk about that formally more next week, but it's good for this discussion. Okay? So, bottom part of this graph, right there at the beginning, right? If we look at the ordered pairs that make up this part of the graph right here, right? X values, what are they doing along this line? They're increasing, and then Y values are increasing as well. That kind of makes sense, right? If we add energy, the particles are going to move faster. But during this section right through here, what do you see is happening at that point? The temperature is constant, staying the same. But are we still putting energy into that system? Yes. Anybody know what happens to water at 0 degrees Celsius? It freezes, or if we're going the other way, it unfreezes, which we call melting. All right?
Nice.
So, during this change of state, the temperature of the substance actually does not change. If we go back to yesterday's lab, not literally in your mind, right? You started off your lab quest, and it started making a graph for you. And that graph went like this, right? That was the first part of the graph. When did this happen? Literally, when did that part of the graph happen? When we were doing what? Not yet.
Put it in the water.
At night.
When we were doing what? When we were taking notes, this happened to your graph.
Yesterday.
What did your lauric acid look like before we started taking notes? It was a liquid. What did it look like when we were done taking notes? It was a solid. What was happening during this section right here? It was changing state. Specifically, it was freezing. So, an important part of answering your questions would be, so see this flat part right here? If you take it back over to the y-axis, which is recording temperature, what are we going to call that flat area temperature? It's the freezing point, right? Or it's the freezing temperature, okay? Now, did your graph hydrogens show up? Were those changes of state? No. Right? Did it go from a solid to a Bose-Einstein condensate?
No, of course.
No. Okay? But when did these flat parts happen here? When we did what?
Added more cold.
Water.
When we put it in the cold water, and then when we put it in the ice. What's happening at those second and third flat parts of your graph?
It's not going anywhere.
It's not going anywhere. Why not?
Because it's colder.
It's what so Katie, you're right. At this point here, this is the temperature of what?
The water.
The water that it was sitting in. It just got cold as the water got. Is it going to get any colder than that? No. And then here, it just got as cold as what? The ice water that it was in. Does it get any colder than that? No. So those flat parts, those aren't changes of state. This one's a change of state because you actually saw it change from a liquid to a solid. Right? These are just things when it, gets to the temperature of the surroundings. But the important part being, though, that during a phase change, the temperature of a substance does not change. Something going from let's say in this case, well, let's go the other way, from a solid to a liquid. What has to happen in order for it to go from a solid to a liquid? Particles need to what? Solid to liquid, particles need to speed up. What else has to happen though? Lose attraction. What has to happen to do their spacing? Less orderly, right? Okay. Think about our analogy of kids in school. If we go back to this picture, what does this point right here represent in your school day? The bell ringing. Right now, what state of matter are you representing? Solid. When you go out there, we said you're representing what? Liquid. But before you transition from the solid state into the liquid state, what do you have to do?
Get up.
You got to get up. You got to do us. You got to get your books together, right? You got to put them in your backpack, right? You got to put your backpack on your back, right? During those times, right, are you actually moving faster per se? You're moving more, but you're not really going that fast. You know what I'm saying? Right? Energy is increasing, but the temperature really isn't changing. Does that make sense? Right? So what's happening during those times? For you guys, that's preparing to go from one class into the hallway. For things going from a solid to a liquid, they're taking care of all those attractions. Notice, bonds is in quotation marks. When water goes from being an ice cube to being a glass of water, does it actually split apart its hydrogens and oxygens? No, but they don't hold on to each other quite as much anymore. That's why it's quote-unquote bonds. Right? We could also substitute in attractions there, and that would be perfectly fine. Okay? But what does that result in? That means that when you're recording the temperature of a substance as it's changing phase, it doesn't actually go anywhere temperature-wise. Okay? Good there? Okay. Let's finish this up here with the phase diagram. The phase diagram is a graph that tells you temperature and pressure detailing the state of matter of a material. As we've said, 10 times already today, what are the two factors that determines the state of matter that a material exists in? Motion and traction, right? We already established, what does temperature tell us about? Temperature tells us about motion, right, or how fast they're going. And that means that pressure is probably going to tell us about what? The attractions. pressure talks about how close those things are, or how tightly they're being squeezed together, which affects the forces of attraction. All right, good there?
Sure.
Okay. So let's take a look at a couple pictures. You're not done yet, everybody. Settle down. It's Friday. Lucky the microphone doesn't pick that up. So. All right. Here is the phase diagram for water, which is on the left of your outline down at the bottom of the back page. So over here on the y-axis, pressure. Over here on the x-axis, temperature. Okay? This value right here, 1 atmosphere, that is the pressure in this room. That's what we call a normal atmospheric pressure. We're pretty close to normal atmospheric pressure. So the particles are kind of being squeezed together, a certain tightness, blah, 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 blah. Okay? If we take a look at this graph, there are 3 regions, right? Over here on the left, what region are you seeing labeled right here? Solid here, liquid in the middle, vapor in the end. Okay? Now, that means, let's take a look at this line right here, this red line. What's happening at this red line? Well, let's talk about at one specific point on that red line. Not the triple point. It's changing state. Changing state from what, Maddie?
Solid to liquid.
This red line right here.
Oh, that red line?
Gas.
Oh, from, just.
Depends on which way you're, sorry. How about maroon? So around this maroon line, let's go maroon. Mauve is, mauve seems more, I think of lighter purple.
And much negative.
Or am I thinking periwinkle? No.
Pink pear.
Super glad this is getting recorded.
Would you say Becca's back?
Some people are saying Becca's backpack.
Actually, Becca's backpack would be a deep rose.
Yeah, thank you.
We need to get a screen here so we can like show this, but
Oh, hey,
anyway.
Periwinkle, that was on
It's
Blue's
definitely-
Clues.
Yeah, periwinkle was the cat on Blue's Clues.
What's the other dog's name?
Magenta, which is kind of weird because
He's a boy.
Magenta's a boy and
That always confuses
but blue is blue and a girl.
Yeah, I
So,
was thinking,
I mean, I mean,
Hey, we don't judge.
I know. I'm saying, like I said, it's probably good that Blue's Clues is trying to break stereotypes. Just
I
kind of.
never thought about it.
But anyway, hey, let's finish this up here. Okay? Because we still have 7 minutes of class left.
No fun.
we're so off the
I just want.
No, I actually have a real cool thing to tell you here.
Go ahead.
Hurry up.
Do it.
Whoa. Easy. All right, so at this point, red dotted line, the one that I drew, this is the pressure in this room. And if we want to go from a liquid phase to a vapor phase, boil something, at this pressure, we would draw our line down, and we end up at what temperature? 100 degrees, okay? Which is the temperature that water boils, here, okay? But let's say we go to someplace like Denver or Salt Lake City or Mount Everest, which is kind of, the altitude is higher, but that affects one of these 2 factors. It affects the pressure. What does it do to the pressure? It drops. The pressure goes down.
Goes down. Just kidding.
Now, hey, the pressure, because there's actually less particles, there's less air up there.
Is that why people have to wear like
Yes.
Yeah, that's
Totally.
why they have to go like a little bit up the mountain, then come back down. Go up.
Now, that being said, okay, if we take a look, right, that line between the liquid phase and the vapor phase, representing boiling, if we intersect the red dotted line and the blue dotted line now, what temperature is water boiling at now?
Like 900.
Not 100, okay? So is the boiling point of water 100 degrees?
Not necessarily.
Because phase changes don't just depend on temperature,
Also based on pressure.
also based on pressure.
Is there anything else we need to know?
For instance, anybody ever go to Spencer's or some other place like that catalog and see something that's called, you ever see like something that's called like a hand boiler? See? So it's kind of fun. It's kind of fun thing. It's a. Well, let me show you what it does.
Okay.
So it's basically just like a glass tube, and it's got like kind of like here, and then there's like funny shapes and stuff like that. But there's got like a green. Sometimes it's got like green or red liquid in it or whatever. Okay. And you hold that bulb in your hand, and the red liquid will start boiling in your hand. Because the pressure inside of it is really, really low, like somewhere down here. Okay, it's like kind of a partial vacuum inside. But when you do that, the temperature at which that water inside, just water with food coloring in it or something like that, decreases. If you get the pressure low enough, the temperature at this intersection of these two sections gets down to approximately 37 degrees Celsius. Anybody know anything that is 37 degrees Celsius?
That's our body temperature.
Your hand is approximately 37 degrees Celsius. Meaning, if the temperature of your hand is enough to cause those particles to move fast enough and break the attraction of the other particles. Because at the lower temperature, or at the lower pressure, how closely are they being squished together?
Very, very, very.
Less pressure means less squishing. Which means, is it harder or easier to break free of the other ones? It's easier. You don't have to put as much energy in. And that's why your hand is enough to boil it. Is it boiling?
Yes.
Yeah.
Yes.
It's turning from a liquid to a gas. It's not what we think of as boiling, but that's the definition of boiling. Because phase changes aren't temperature dependent. They're dependent on temperature and pressure. Alright? So, to wrap this up, that helps, definitely. So, yeah, but that's kind of what we're talking. We will wrap this up on Wednesday, talk about triple points, and talk about some other cool examples of the temperature pressure thing. Have a good weekend, everybody.